Hey everybody, Greg here. How are you doing? Well, it's Tuesday night, it's midweek, and I wanted to go over a few things from Monday and Tuesday just to clarify because as we go into the course, knowing about this normal distribution and the central limit theorem is pretty important. So I looked at the post last night and I'm going to go in and look at them all tonight. I'm sure everybody's doing just fine. It's been a long day for me. I know you're tired too, but go in every night and do just a little bit. And let's just go over what hopefully we would have found. Now, when you laid out your deck of cards, you were right, and some people put an actual histogram in there of the cards. And the distribution was not normal. It was skewed to the right, okay? So the distribution of the cards looked like this. All right, there it is right there. And that's not exact, but I think when you looked at the mean of the cards you had, I think it was 4.3. Well, then everybody took a random sample of their cards and posted their sample, and then everybody was to take all of those sample means and find the mean of that. And here's what happens. It's kind of counterintuitive. All right, if you were to take, this is what the central limit theorem says. If you were to take every possible sample size of n, let's say you were to take out of that deck of cards, or out of the cards you had, every possible different sample of size 4, and then find the mean of each one of those samples, what you would find is that the sample means would not be skewed to the right as the population is. The sample means would be normally distributed. So, even though my drawing's a little crude here, even though the population mean is right over here, and I think it was about 4.3, and this distribution is not normal and it's skewed to the right, if you took the mean of all possible samples, you would get what's called a sampling distribution, and that sampling distribution would have precisely the same mean as the population mean, except all of the sample means would be normally distributed even though the population was skewed to the right. And that seems counterintuitive. You would think that the means of all the samples would be skewed to the right, but they're not. And that's a little interesting experiment. It's not too hard to do on your own. And we've done that a few times before. But the key is the central limit theorem, the fact that all possible sample means are normally distributed, even if the population is skewed, allows us to make accurate predictions about the population mean from samples. And that was the point of the whole 2 days. So if you got that out of it, that's pretty good. A couple of other things to note. I asked you a couple of questions there in a post about the normal distribution. And here are the important things to take away. What actually causes a variable to be distributed normally? Well, let's take, first of all, I asked about the speed of light. And the speed of light has been exactly the same since the beginning of the universe. It never changes. It can't, and it never will. But if you go back 500 or 600 years ago, when people started to measure the speed of light, sometimes their measurements were a little fast, sometimes their measurements were a little slow. And the reason for that is that the way they measured them, there was random error. Sometimes they were high, sometimes they were low. And you think about the instruments they had to measure the speed of light 600 years ago, they weren't very accurate. So people actually thought the speed of light varied, but it doesn't. It's precisely the same as it has been for 13 billion years. But it was the measurements that varied normally. Now, the same concept can be applied. Let's say you're throwing darts at the middle of a dartboard. So let's take a look again. So you're throwing darts at the middle of a dartboard. Now, random error is going to cause some darts to go right, some darts to go left. Fewer still that far right, fewer still that far left. But the random error is going to form a normal distribution, even though most of your darts hit right in the middle. And there's no reason for the random errors to the right or the left, except that it's purely the random process itself. So a normal distribution occurs when a variable has randomly distributed highs and lows for no known reason. Okay, so here's an example. Let's say you take the height of 16-year-old boys in a middle-class suburb in America. And so whatever the height of 16-year-old boys is, let's say it's 60 inches. Now, the heights of the boys will vary due to random genetic influences. Some will be a little high, some will be a little low. But basically, there's no cause for the heights of the boys to be any different. Okay, it's just some are a little taller, some are a little shorter. That's a random process. And so the heights of male teenage boys in the United States is normally distributed. Now, let's say you go to another country and you were to measure the heights of teenage boys. You might find that it looks more like this. Okay? So the mean height of the boys is to the right of the mode. Now, how does that happen? Well, it happens because we can identify specific causes. Maybe some of the boys are in a different economic strata, and so they eat better. And that is what causes the distribution to be skewed to the right. Whereas this is a random process, this process has causes associated with it. So here's one more example. In the United States, the distribution of income is not normal. The mean, median, and mode is not $45,000. I think $45,000 is the median income in the United States. In the United States, the distribution of income is somewhat skewed to the right. Now, of course, there's a big debate now on the distribution of income. And the distribution of income is skewed to the right a little, but there's a lot of variation in opinion as to how skewed it is. But nonetheless, it is slightly skewed to the right, meaning the mean income is slightly higher than the median, which is slightly higher than the mode. And that's just the way it is for various tax and economic reasons. But the key to keep in mind is that a variable is not normally distributed because of the central limit theorem. It's normally distributed simply because random processes would make a variable a little high or a little low. Okay? And that's important to keep in mind as we go on into the course. So the key here is the central limit theorem says that the mean of all possible sample means is exactly equal to the population mean, except the sample means are distributed normally, even if the population is not. And you can go in and Google some of this and take a look. The central limit theorem is pretty fascinating. The reason that we did it is because it's what allows us to make predictions about the population. Now, as we go into the second part of the week, you're going to be developing what are called confidence intervals. And a confidence interval is when you take a sample from a population. Let's say you want to find out what the mean length of cat's tails are in a certain county in the United States. So you take a sample of cats and you measure their tails, and you get a mean tail length. Okay, well, from the sample, from the standard deviation of the sample, and from the mean of the sample, you create what is called a confidence interval. And that confidence interval tells you the mean of the lengths of the cat's tails in the whole county. It tells you a range which within which that mean must fall, and it's only based on the sample. So it's a mathematical process. So maybe our confidence interval is, the endpoints of our confidence interval are between 7 and 10. That means we can be pretty sure based on the sample that the mean length of the cat's tails is between 7 and 10. We can't be any closer than that because we've only taken a sample. But we'll explain that more as we go on. So the two parts of the week work together. It's because of the central limit theorem that we can create what are called confidence intervals. And we'll work on confidence intervals in the second half of the week. So I can't think of anything else. I just wanted to clear that up. If you want to spend a little more time on that central limit theorem, it is really something that's important to understand. One of the things you have to keep in mind is what we talked about in our PLC. Everything you're doing is working towards your dissertation. So being able to understand and how to see if a variable is normally distributed is really important in all quantitative research. So everybody's doing a great job so far this week. The second half of the week is pretty straightforward again. It's pretty calculator based. Just put the numbers in the calculator and report the numbers and then try and explain what they mean. So I know you're all working hard, and thank you very much. We'll continue and onward with the journey. Okay, have a nice evening. Bye.